Download this code from codegive.com, link in the description below. OK, let's dive deep into SQL optimization, focusing on the background, CMU's approach, and practical code examples. This will be a comprehensive guide, covering the theoretical foundations, optimization techniques, and how to apply them using SQL Server as our primary database platform. Understanding the need for SQL optimization. Before we jump into techniques, it's crucial to understand why SQL optimization is essential. Performance slow queries can cripple an application. Users expect quick responses. Slow reports can delay decision-making. Optimization aims to reduce query execution time. Scalability. A well-optimized database can handle a larger workload with the same hardware. Without optimization, you might need to upgrade hardware constantly, which can be expensive. Resource consumption. Poorly written queries can consume excessive CPU, memory, and I/O resources. Optimization minimizes resource usage, freeing them for other processes. Cost. In cloud environments, AWS, Azure, GCP, database usage is often billed based on resource consumption. Reducing resource consumption directly translates to cost savings. Overall application experience. A responsive database leads to a smooth and enjoyable user experience. 2. Background: the SQL query processing pipeline. To optimize queries effectively, it's essential to understand the stages a SQL query goes through within the Database Management System, DBMS. 1. Parsing. The SQL query is checked for syntax errors. The DBMS ensures the query conforms to the SQL standard and its specific dialect. 2. Semantic analysis. The DBMS verifies that the tables, columns, and other database objects referenced in the query exist and that the user has the necessary permissions. 3. Optimization. Query optimization. This is where the magic happens. The query optimizer analyzes the query and generates multiple execution plans. Each plan represents a different way to retrieve the data. The optimizer estimates the cost, example CPU time, I/O operations, of each plan and chooses the plan with the lowest estimated cost. This is a cost-based optimization. 4. Code generation. The chosen execution plan is translated into machine executable code, or bytecode in some cases. 5. Execution. The code is executed, retrieving the data from the database. 3. CMU's database group and query optimization research. Carnegie Mellon University, CMU, has a world-renowned database group that has made significant contributions to query optimization and database systems research. Here are some relevant concepts and areas where CMU has made a mark. Cost-based optimization. CMU researchers have significantly advanced the understanding and development of cost-based optimizers. This involves accurately estimating the cost of different execution plans. This is the core idea of many database systems. Join ordering. Determining the optimal order in which to join multiple tables is a crucial aspect of query optimization. CMU has contributed to algorithms for join ordering, including techniques like dynamic programming and randomized search. Query rewrite rules. CMU has explored query rewrite rules, which transform the original query into an equivalent but potentially more efficient form. Examples include pushing down predicates, rewriting subqueries, and applying algebraic transformations. Adaptive query processing. This area deals with adjusting the execution plan during runtime based on observed data characteristics. For example, if a join operator encounters unexpected data skew, the system might switch to a different join algorithm. CMU has been active in this research area. Column-oriented databases. CMU has been influential in the development of column-oriented databases, which are optimized for analytical queries. 4. Key SQL optimization techniques. Now, let's explore the essential SQL optimization techniques you can apply. 1. Indexing asterisk. What it is an index is a data structure that speeds up data retrieval. It's similar to an index in a book. Instead of scanning the entire table, the DBMS can use the index to quickly locate the rows that satisfy the query. How to use it. Create indexes on columns that are frequently used in where clauses, join conditions, and order by clauses. Example, SQL Server. Considerations. Don't over-index. Too many indexes can slow down insert, update, and delete operations because the indexes must be updated as well. Consider clustered versus non-clustered indexes. A clustered index determines the physical order of the data on disk. There can be only one clustered index per table. Regularly review and drop unused indexes. 2. Query rewriting. What it is transforming the original query into an equivalent but potentially more efficient form. Techniques. Pushing down predicates. Move filtering conditions as close as possible to the data source. This reduces the amount of data that needs to be processed in subsequent stages. Rewriting subqueries. Subqueries can often be rewritten as joins, which can be more efficient. Removing unnecessary joins. If a join doesn't contribute to the final result, remove it. Simplifying where clauses. Simplify complex where clauses by applying Boolean algebra rules. Example, SQL Server. Important note. The join will likely be more efficient than the in subquery, especially as the number of rows in orders grows. 3. Join optimization. What it is optimizing how tables are joined together. Techniques. Choosing the correct join type. Use inner join, left join, right join, or full outer join based on the desired result. Avoid full outer join unless absolutely necessary, as it can be expensive. Join order. The order in which tables are joined can significantly impact performance. The optimizer typically chooses the best order, but you can sometimes influence it using query hints. Use with caution. Join the smaller tables first. Using appropriate join algorithms. Different join algorithms, example nested loops, hash join, merge join, are suitable for different data sizes and conditions. The database optimizer chooses the appropriate algorithm. Example, SQL Server. Nested loops. Simple to implement, good for small tables and indexed lookups. Hash join. Builds a hash table on one table and probes it with the other table. Good for large tables and equijoins. Merge join. Requires both tables to be sorted on the join column. Good for large tables that are already sorted or can be sorted efficiently. 4. Data types. What it is choosing the correct data types for your columns. How to use it. Use the smallest data type that can accommodate the data. For example, use int instead of bigint if the values will never exceed the range of int. Use varchar instead of char if the length of the strings varies. Use date or datetime too instead of storing dates as strings. Why it matters. Smaller data types consume less storage space, improve index performance, and reduce memory usage during query execution. 5. Avoid using select asterisk. Asterisk why it's bad asterisk select asterisk retrieves all columns from the table, even if you only need a few. This can lead to unnecessary I/O and increased network traffic. Asterisk best practice asterisk specify the columns you need explicitly. Asterisk example asterisk. 6. Limit the use of cursors asterisk. Asterisk what they are asterisk cursors allow you to process rows one at a time. They are often used in procedural code to perform operations on each row in a result set. Asterisk why they're often slow asterisk cursors are generally much slower than set-based operations. Asterisk alternatives asterisk try to use set-based operations, example update statements with where clauses, insert into select statements, instead of cursors whenever possible. 7. Use stored procedures asterisk. Asterisk what they are asterisk precompiled SQL code that is stored in the database. Asterisk benefits asterisk. Asterisk performance asterisk stored procedures are precompiled, so they execute faster than ad hoc SQL queries. Asterisk security asterisk stored procedures can help prevent SQL injection attacks. Asterisk maintainability asterisk stored procedures make it easier to maintain and update your database code. Asterisk example, SQL Server. 8. Analyze execution plans asterisk. Asterisk what they are asterisk execution plans show how the DBMS intends to execute a query. They provide valuable insights into the performance of the query. Asterisk how to use them asterisk use the query analyzer tool in your database management system, example SQL Server Management Studio, MySQL Workbench, to view the execution plan. Asterisk what to look for asterisk. Asterisk table scans asterisk table scans are generally less efficient than index seeks. If you see a table scan, consider adding an index. Asterisk key lookups can be expensive. They occur when the index does not contain all the columns needed for the query, and the DBMS has to go back to the table to retrieve the remaining columns. Consider creating a covering index. Asterisk sort operations can be slow, especially for large data sets. Try to avoid sorting if possible, or optimize the sorting process. Asterisk expensive operators asterisk identify the most expensive operators in the plan, example hash joins, merge joins, and try to optimize them. Asterisk missing indexes asterisk the execution plan may suggest missing indexes. Asterisk example, SQL Server. Asterisk in SQL Server Management Studio, enable include actual execution plan before running the query. Asterisk after the query executes, the execution plan tab will show the graphical representation of the plan. 9. Update statistics asterisk. Asterisk what they are asterisk statistics are information about the distribution of data in tables and indexes. The query optimizer uses statistics to estimate the cost of different execution plans. Asterisk why they're important asterisk outdated statistics can lead to inaccurate cost estimates and poor query plans. Asterisk how to update them asterisk. Asterisk considerations asterisk configure automatic statistics updates in your database. 10. Partitioning asterisk. Asterisk what it is asterisk dividing a large table into smaller, more manageable pieces called partitions. Asterisk benefits asterisk. Asterisk improved query performance asterisk queries can be targeted to specific partitions, reducing the amount of data that needs to be scanned. Asterisk easier data management asterisk partitions can be archived, backed up, and restored independently. Asterisk faster data loading asterisk data can be loaded into partitions in parallel. Asterisk example, SQL Server. 11. Materialized views asterisk. Asterisk what they are. Asterisk a materialized view is a pre-computed result set that is stored on disk. Asterisk benefits. Asterisk significant performance improvement. Asterisk queries that access the materialized view can be answered much faster than queries that have to compute the result set from scratch. Asterisk suitable for complex, read-heavy queries. Asterisk materialized views are especially useful for complex analytical queries that are executed frequently. Asterisk example, SQL Server. Asterisk key considerations. Asterisk materialized views require storage space. Asterisk the materialized view needs to be updated whenever the underlying data changes, either manually or automatically. SQL Server provides automatic materialized view maintenance. VCMU-inspired approaches and further considerations. Asterisk cost modeling. Asterisk deeply understand how your DBMS estimates the cost of different operations. CMU's research emphasizes accurate cost modeling as crucial for effective optimization. Experiment with different settings to see how they impact query plan choices. Asterisk join cardinality estimation. Asterisk the optimizer needs to estimate how many rows will result from a join operation. Inaccurate estimates can lead to suboptimal plans. CMU has researched techniques for improving cardinality estimation. Asterisk learning-based optimization. Asterisk some recent research explores using machine learning to learn the characteristics of the workload and automatically tune the optimizer. Asterisk database design. Asterisk good database design is the foundation of good performance. Normalize your database to reduce data redundancy and improve data integrity. Asterisk hardware. Asterisk ensure you have sufficient hardware resources, CPU, memory, disk I/O, for your database workload. 6. Practical steps for optimization. 1. Identify slow queries. Asterisk use monitoring tools, example SQL Server Profiler, extended events, performance counters, to identify queries that are taking a long time to execute. 2. Analyze execution plans. Asterisk examine the execution plans for the slow queries. Look for the problems mentioned earlier, table scans, key lookups, sorts, etc. 3. Apply optimization techniques. Asterisk use the techniques discussed above, indexing, query rewriting, etc., to improve the performance of the queries. 4. Test and measure. Asterisk after making changes, test the queries to ensure that they are actually faster. Use performance testing tools to measure the impact of the changes. 5. Iterate. Asterisk optimization is an iterative process. You may need to repeat steps 2 to 4 several times to achieve the desired performance. 7. Code example, optimizing a common query. Let's assume we have a customers table and an orders table, and we want to find the customers who placed orders in a specific date range, along with their order details. Optimization steps. Asterisk. 1. Indexing. Asterisk ensure that there are indexes on orders.customer ID and orders.order date. 2. Covering index, if needed. If the query frequently retrieves order ID and total amount along with order date, consider a covering index. 3. Update statistics. Asterisk. 4. Analyze execution plan. Asterisk after applying the indexes and updating statistics, re-examine the execution plan to verify that the indexes are being used and that there are no expensive operations. 5. Query rewrite. If the customer name in the customers table is very large, and the orders table has many records, you may be able to optimize by joining onto a subset of the customers table. Important considerations for code example. Asterisk. These optimizations are specific to this query and data model. The best optimizations will vary depending on your specific workload. Always test the performance of your queries before and after making changes to ensure that the optimizations are actually improving performance. Pay attention to the sizes of the tables involved. Different techniques are more appropriate for small tables versus large tables. 8. Conclusion. SQL optimization is a complex but rewarding endeavor. By understanding the query processing pipeline, applying appropriate optimization techniques, and continually monitoring and tuning your queries, you can significantly improve the performance, scalability, and resource utilization of your database applications. CMU's research has provided valuable insights into cost-based optimization, join ordering, and other areas that are essential for building high-performance database systems. Remember to approach optimization as an iterative process, continually learning and adapting your techniques to the specific characteristics of your workload. Okay, let's dive deep into SQL optimization, covering the background, CMU's approach, and concrete code examples. This will be a comprehensive guide. SQL optimization, why bother? The core problem SQL, structured query language, is a declarative language. You tell the database what data you want, not how to get it. The database's query optimizer is responsible for figuring out the best execution plan. Inefficient plans lead to slow queries, high resource consumption, CPU, memory, I/O, and poor overall application performance. Scalability even if a query runs fast on a small data set, it can become painfully slow as your data grows. Optimization is crucial for ensuring your application scales effectively. Concurrency slow queries block resources, impacting other concurrent operations. Optimized queries allow for higher throughput and better responsiveness. Cost cloud database services often charge based on resources used, CPU, storage, I/O. Inefficient queries can lead to unexpectedly high bills. User experience slow loading data frustrates users. Optimization contributes directly to a better user experience. 2. SQL query processing pipeline. Understanding the query processing pipeline is essential for optimization. Here's a simplified breakdown. 1. Parsing *. The SQL query is parsed to verify its syntax and semantics. It's checked for errors, example misspelled table names, invalid syntax. 2. Semantic analysis *. The parser builds an internal representation of the query, often a parse tree or abstract syntax tree, AST. This stage validates table and column existence, data types, and user permissions. 3. Logical optimization *. The query optimizer applies rules to transform the logical query plan represented by AST into an equivalent, but more efficient plan. Common transformations include predicate pushdown moving where clause conditions closer to the data source. Join reordering determining the optimal order in which to join tables. Subquery unnesting converting subqueries into joins. View materialization deciding whether to pre-compute and store the results of a view. 4. Physical optimization, plan generation. The logical query plan is translated into a physical query plan. This involves algorithm selection choosing specific algorithms for operations like joins, example hash join, merge join, nested loop join, and sorting. Access path selection deciding how to access data, example full table scan, index scan. Operator ordering determining the final execution order of the physical operators. 5. Plan cost estimation the optimizer estimates the cost, example CPU usage, I/O operations, memory consumption, of various physical plans. Cost estimation is based on database statistics about data distribution, index cardinality, and table sizes. 6. Plan selection *. The optimizer chooses the physical plan with the lowest estimated cost. 7. Execution *. The database engine executes the selected physical plan to retrieve the requested data. 8. Result delivery *. The results are returned to the user or application. 3. SQL optimization techniques, a practical toolkit. Here's a breakdown of common optimization techniques. Indexing purpose speed up data retrieval by creating sorted structures that allow the database to quickly locate specific rows based on the indexed columns. Considerations indexes improve read performance but can slow down writes, inserts, updates, deletes, because the index needs to be maintained. Don't over-index. Example, MySQL. Predicate pushdown purpose filter data as early as possible in the query processing pipeline. Reduce the amount of data that needs to be processed by subsequent operations. How it works move where clause conditions to the tables they reference, ideally before joins. Example, implicit. Join ordering purpose minimize the size of intermediate results during joins. Joining smaller tables early reduces the amount of data that subsequent joins have to process. Heuristics start with the table that has the most restrictive where clause condition. Join tables in an order that minimizes the number of rows passed to the next join. Example, often implicitly handled by the optimizer, but hints can be used. The optimizer should choose to filter customers first based on the city index. Algorithm selection, join types. Nested loop join simple, but inefficient for large tables. Suitable when one table is very small. Hash join builds a hash table on one table, the build table, and then probes it with rows from the other table, the probe table. Very efficient when the build table can fit in memory. Merge join, sort merge join requires both tables to be sorted on the join key. Efficient when the tables are already sorted or when sorting is relatively inexpensive. Example, hints, if supported by the database. Note using join hints is generally discouraged because it overrides the optimizer's choices. Only use them if you have a very good understanding of the data and query execution. Subquery optimization purpose eliminate correlated subqueries, which can be very slow. Techniques unnesting convert subqueries into joins. Materialization precompute the results of a subquery and store them in a temporary table. Example data type optimization purpose use the smallest appropriate data type for each column. This reduces storage space and improves performance, especially when joining tables. Example instead of using varchar 255 for a column that only contains short strings, use varchar 50 instead of bigint when int will suffice. Partitioning purpose divide a large table into smaller, more manageable pieces. This allows the database to scan only the relevant partitions when querying data. Example, MySQL, partitioning by date. Denormalization, use with caution. Purpose add redundant data to tables to reduce the need for joins. This can improve read performance but makes writes more complex and can lead to data inconsistency if not managed carefully. Example instead of joining customers and orders to get the customer's city for each order, you could add a customer_city column to the orders table. Query rewriting purpose restructure a query to be more efficient without changing its results. This can involve using different SQL constructs or applying algebraic transformations. Example replacing or with union all when appropriate. Statistics management purpose provide the query optimizer with accurate information about the data distribution in your tables. This allows the optimizer to make better cost estimates and choose more efficient plans. Action regularly update statistics using commands like analyze table, PostgreSQL, MySQL, or update statistics, SQL Server. 4. Carnegie Mellon University, CMU, Approach to SQL Optimization, LEO, Learning Optimizer. CMU has been at the forefront of research in query optimization, including the development of learning-based optimizers. One prominent example is LEO, Learning Optimizer. Key idea use machine learning to learn from past query execution experience and improve future query plan selection. Traditional optimizers rely heavily on cost models that are often inaccurate, especially for complex queries or unusual data distributions. LEO attempts to learn a more accurate cost model. How it works, simplified. 1. Training data LEO observes the execution of real-world queries and collects data about their actual performance, example execution time, resource consumption, for various plan choices. 2. Feature extraction it extracts features from the query, the database schema, and the execution environment, example number of tables involved, join types, statistics about the data. 3. Model training it uses machine learning algorithms, example regression models, neural networks, to train a cost model that predicts the performance of a query plan based on the extracted features. 4. Plan selection when a new query arrives, LEO uses its learned cost model to estimate the cost of different physical plans and selects the plan with the lowest predicted cost. 5. Feedback loop the actual performance of the chosen plan is observed and used to further refine the cost model. This creates a feedback loop that allows LEO to continuously improve its performance over time. Advantages of learning-based optimization adaptation learns from real-world data and adapts to the specific characteristics of the workload and database environment. Accuracy can often produce more accurate cost estimates than traditional cost models. Robustness less susceptible to errors in database statistics or assumptions about data distribution. Challenges data requirements requires a significant amount of training data to build an accurate cost model. Complexity learning-based optimizers are more complex to implement and maintain than traditional optimizers. Overfitting risk of overfitting the cost model to the training data, which can lead to poor performance on unseen queries. Example of LEO in action, conceptual. Let's say your database is running a query with a join between tables A and B. A traditional optimizer might pick a hash join based on its understanding of the table sizes and available memory. However, LEO might have observed that in the past, for queries with similar characteristics, example similar join predicates, data types, a merge join performed much better. Therefore, LEO would select a merge join. Crucially, it learns this from experience, not just from a predefined cost model. Imagine you have the following query. The optimizer believes a nested loop join is the best option, cost, 100. LEO monitors the actual execution of this query. It determines a hash join runs faster than a nested loop join, cost, 60. It updates its cost model to prefer hash joins for similar queries based on its learned experience. V. Practical steps for SQL optimization. 1. Understand your workload *. Identify the most frequently executed and most time-consuming queries. Focus your optimization efforts on these queries. 2. Use explain *. Use the explain command, or its equivalent in your database system, to examine the query execution plan. This will reveal how the database is executing your query and identify potential bottlenecks. Look for full table scans, inefficient join algorithms, and missing indexes. 3. Profile your queries *. Use profiling tools to identify the specific parts of your query that are taking the most time. This can help you pinpoint the areas that need optimization. Many database systems have built-in profiling capabilities, example SQL Server Profiler, MySQL Performance Schema. 4. Analyze table and index statistics *. Ensure that your database has up-to-date statistics about the data distribution in your tables and indexes. 5. Apply optimization techniques * based on your analysis of the query execution plan and profiling results. Apply the appropriate optimization techniques, example indexing, predicate pushdown, join reordering, query rewriting. 6. Test and measure *. After making changes, test your queries to ensure that they are running faster and that you haven't introduced any new performance problems. Use metrics like query execution time, CPU usage, and I/O operations to measure the effectiveness of your optimizations. 7. Iterate and monitor *. SQL optimization is an ongoing process. As your data changes and your workload evolves, you will need to revisit your queries and make further optimizations. Set up monitoring to track query performance and identify any regressions. 6. Code examples across different databases. These are examples, the specific syntax and features may vary. *PostgreSQL ***, MySQL **, SQL Server **. 7. Key takeaways. *SQL optimization is critical for performance, scalability, and cost efficiency. Understand the query processing pipeline to identify optimization opportunities. Use indexing, predicate pushdown, join reordering, and query rewriting to improve query performance. Monitor query performance and iterate on your optimizations. CMU's Leo represents a cutting-edge approach to optimization using machine learning to adapt to the characteristics of your data and workload. Use explain to understand execution plans and identify bottlenecks. Statistics are crucial. Keep them up to date. This comprehensive guide provides a solid foundation for understanding and implementing SQL optimization techniques. Remember that optimization is an iterative process, and the best approach will depend on your specific database system, data characteristics, and workload. Good luck.